So Mathieu, whenever you want, you can start.
Okay, thank you very much for the organization and for preparing everything. So, hi everyone, welcome to this fifth lecture. So, the goal of this lecture will be to discuss deep learning methods, part 2, for PDEs and master equations arising in mean-field games. But before doing that, I will finish what we didn't completely cover in the previous lecture. So let me go back to the previous lecture slide, which was lecture 4. And it was about a direct approach for mean-field control, meaning that we parameterize the control and try to minimize the cost directly using stochastic gradient descent. And another approach, which is to take forward-backward SDs of Makin-Vlasov type, for example, coming from a mean-field game, rewriting this as an optimal control problem of mean-field type, and then using the previous method. So I will directly, jump to this part. I would like to finish this part because we stopped at one example. I would like to show a piece of code to solve this example, and then mention 2 extensions. After that, we will move on to lecture 5, the slides of lecture 5. So the approach that we discussed last time, which was introduced by Wayne and co-authors, called the deep BSD method, consists in taking backward stochastic differential equation with a terminal condition and trying to guess the initial value of y0. In the original paper, I think it is done for a fixed x0. So you can take x0 equals a given value, or you can take it distributed according to some distribution, in which case y0 should be a function of x0 that you try to learn. And you also try to learn z, which is this term here in front of the dw for y. So you try to learn these 2 functions, and it becomes really an optimal control problem, where the cost is how far you are from satisfying the terminal condition. So you can extend that to the case of mean-field interactions. This is done on this slide. And here, of course, there is a question of what to do with the distribution. So in some cases, you can just approximate the distribution by an empirical distribution and then estimate the quantities you need to estimate, for example, the mean or the mean of some function of x. So one typical example is, imagine that this function b depends on L, but only through some expectation of a function of xt. Then this is something that you can approximate using a finite number of samples pretty well. For example, something like this, right? Of course, if you have a very complicated dependence on the law of x, then maybe you want to use other techniques than just an empirical distribution. But for now, I will stick to this in this presentation. So this was a summary of the method. The 2 neural networks are in red here, so y0 and z. And for z, here at least, the way I present it, this is the neural network z parameterized by some parameters, let's say theta z, evaluated at t0, and then you evaluate it at each of the x0 I for different I. And here, same thing, you take z parameterized by the same parameters at time t1, and you evaluate it at xi t1. So in fact, in the code I'm going to show next, so this should be a vector for I equals 1 to n. But this vector is treated, somehow you don't need to do it coordinate by coordinate. You don't need to apply the neural network coordinate by coordinate for different xi. This is going to be done automatically. So TensorFlow automatically applies the neural network on each coordinate. This is what happens when you have a batch of samples. You can apply the neural network directly to the whole batch at once. Okay, so I discussed this example, which I think is really a nice example to test if you have a numerical method for FBSDEs. This is really a nice example. And for each value of rho, you try to solve the problem. So yesterday we stopped at this example. So I will really restart from here. This is an example of a model for interbank borrowing and lending. So in this case, if we were to write the n-player game, each player would be a bank or a financial institution represented by the state of its log reserves. So the fact that you have log reserves is convenient because it takes values between negative infinity and positive infinity. So you don't need to put any boundary constraint or boundary condition. So xt evolves in the real line. Now, how does X evolve? So in this model, so you can check the paper to have more explanations. But in this model, you have a mean reverting term, which is interpreted as the interactions between one bank and the other banks. So if you are above the mean, you are going to lend money to other people, and if you are below the mean, you are going to borrow money. Alpha t is a term of borrowing or lending to a central bank, but borrowing or lending, particular borrowing to a central bank will have a cost, and so you don't want to take a very large alpha t. Then there is idiosyncratic noise, meaning noise specific to the agent, and there is common noise, which affects everyone. So this is something that we find in many macroeconomic models, common noise, common shocks affecting everyone. So maybe you have the stock, the value of a stock, and suddenly there is a news coming out and it affects the value of the stock. So everyone who has invested in the stock will be affected immediately. So this is really common noise affecting everyone. Then in the cost, you see there is a mean reverting term. And here there is a term which is a little bit peculiar, maybe. This term, so Q is a constant, and you see the product of alpha t and m bar minus xt. So one way to think about this is if xt is below m bar, then this part is negative. Because of the minus sign, you have something positive, but you are trying to minimize, right? We want to minimize the cost. So in that case, you are going to take alpha t small, right? So if xt is smaller than m bar t, then you are going to take, I mean, just by looking at this term by itself, you are going to take alpha t, negative. Sorry, so let's do it again. Xt is smaller than m bar t, so this term is positive. Because of the minus sign, we get something negative, and you try to minimize, so you are going to take alpha t very positive. Positive and large, intuitively. Up, alpha t, positive and large. Of course, there is a balance with the other terms. So what does it mean? It means that when you are below the mean, you will tend to take alpha t positive, meaning you will borrow money. How do I see that you borrow money? Because here you have plus alpha t, so you are going to increase your log reserve. Okay, so you can spend some time thinking about the interpretation of this model. And in fact, in the paper of Carmona, Fouque, and Sun, they have a whole analysis. It's a linear quadratic problem. And so you have an analytical solution. And in fact, in this case, it's really analytical because you can solve the Riccati equation explicitly. So we use that as a benchmark here to test this shooting method, deep shooting method, let's say, for FBSDs of Makin-Vlasov of type. So you train the neural network, and then you plug it in your dynamics. So you learn Y and Z. So you the neural network for the FBSD system, what it gives you is a neural network for Y0, and a neural network for Z. Based on this, you can recover a candidate alpha for the control. Then you take this candidate alpha, you plug it in your dynamics for X, and this is what you see. Of course, it's stochastic, so we take several realizations. Here, 2 realizations, starting from different position and excited by different noises. And you see that, well, the solution, so let's look at this one, for example, X1, it's one of the possible realizations. Then the trajectory obtained by the algorithm, meaning after the control we have learned by using the algorithm, matches very well the one controlled by the true equilibrium control coming from the ODE solution. So you have the blue line and the red lines that really overlap. For the backward equation, it's quite precise, but you see there is a bit more of discrepancy. And this is probably due to the fact that you try to solve the BSD, but using a forward equation. So you try to guess the initial point and you shoot for the terminal condition. So if you make a little bit of error at the beginning, maybe it will stay there and it may accumulate. So in general, you may see a bigger error in the backward than in the forward. And you can be a little bit more precise if you want. So you can, for example, measure the distance. So here it looks like it's really overlapping, but maybe there is a tiny distance between the two. So you can measure this distance in the forward equation, in the backward equation over many realizations. And you can, in this way, estimate the error, for example, the L2 error that the algorithm is making, or that the algorithm is making in terms of the FBSD. So here, we played with the number of time steps, the number of particles in the system, and you see that when you take more particles or more time steps, it gets better. So let me now show you this code briefly. Okay, so I need to. Okay, I need to find a way to change. Okay, so I think it's this one. So here, in principle, you can see my screen with the code. The structure is, there is a part for the problem formulation, a part for the DBSD solver, the benchmark solver, so the ODE, and then the training procedure and some plots. And again, for this notebook in particular, I would like to thank Yuchen Zhu, who helped me to prepare this, and he included more explanations. So you have the systemic risk model. So here you have all the parameters for the mean field gains, and you have the drift for the forward equation and the drift or the driver for the backward equation. So you remember when we did the direct approach, you had the drift for the forward, the running cost, the terminal cost. Here it's different because we don't have a running cost anymore, but we have the driver for the backward equation. So you need to compute this by hand. What is the drift for your forward equation? What is the drift for your backward equation? And what is the terminal cost? So this will be just the penalty for not matching the terminal condition. Then the DBSD solver or FBSD solver here has so a few important functions. The sampling, so you sample X0, you sample DW. If you have common noise, you also sample DW0. There is a loss function here. So what is the loss function? Well, you have a loop in time where you simulate X and you simulate Y. So basically you are simulating your forward processes because now both of them are forward. And at the end, you define the loss, which is equal to the distance between Y and the target, which is your terminal cost, basically. And you would like to match the terminal cost. Sorry, so final cost is really the final cost in the mean field game. And in order to get the error, you do Y minus the target, and usually we square it. Then you have one gradient step, and you have this train function, which basically iterates one step of gradient descent. The benchmark solver, I will skip it, but it uses the ODE system. So we have discussed that in the second lecture. So you see, I keep reusing again this linear quadratic example as a benchmark because it's really convenient. And then, so here we initialize the neural network. In fact, the neural networks, because we have three of them. We have one for Y, we have one for Z, and because we have common noise in this example, we also have, in principle, a neural network for Z0. It turns out that in this example, Z0, you can actually get rid of it, but in principle, when you take a meaningful game with common noise, you are going to have three neural networks, at least with additive DW0 as a common noise. So here we print the architecture for one of the neural networks. You see there are two hidden layers with 100 neurons on each. And here the last layer is one-dimensional output because this is a one-dimensional problem. So you see the number of parameters here is already pretty high, right? Because we know that the solution is going to be almost linear, right? Because it's a linear quadratic problem, but we over-parameterize. In about 1,000 iterations, you see that the loss decreases. This is for this choice of hyperparameters. So you can play with hyperparameters, architecture, learning rate, initialization, etc. And you may get different results. So this is just an illustration. This is the plotting function, so I will skip this. And here you can see the training loss in red. So the x-axis is the iterations, and in blue you see the validation loss or the testing loss. So every I don't know 100 iterations, we take a batch of points, a batch of so random points, so x0 and the increments of the Brownian motions that have not been seen during training, and we evaluate the current neural network, and we compute the loss. And you see that it decreases, even sometimes below the training loss. Then we can do similar plots to what I have shown you earlier. So you take the neural network that you have obtained after training. So this is a neural network, actually three neural networks for Y, for Y0, for Z0. From here, you can deduce the optimal control because this is the argmin or argmax of the Hamiltonian. You plot this in your dynamics and you simulate some trajectories of X, and you see that they match the one obtained when you use the true equilibrium control from the ODE system. You do the same thing for the backward equation, and here again you notice a little bit more of a discrepancy between the two, between the ODE solution and the solution from the deep solver. But you can improve this by taking more points, finite time discretization, etc., etc. So I don't know if there are any questions on this deep BSD approach. So I will take this as a no question, but otherwise feel free to post them in the chat and I will answer as soon as possible. So let me go back to the slides here. Okay, so this was the example about convergence. So there is a proof of convergence by Han and Long for the standard DBSD method, meaning non-mean field, and an extension to finite player games. These proofs of convergence, what we mean by proof of convergence here is something like if you make the loss small, meaning the terminal condition is small, I mean, it's almost matched, then you are approximately solving the FBSD. Okay, but it's not a proof of convergence, for example, of stochastic gradient descent or other errors. I think that actually in this paper, if I'm not mistaken, they analyze also the time discretization. So there are several questions when we talk about convergence of these methods. and some aspects have been addressed, but there is still a lot to explore and to analyze, I think. And in the case of Makin-Vlasov, not much has been done, in particular because, as I mentioned earlier, the problem is quite complicated because you control the volatility. And in Makin-Vlasov control problem, controlling the volatility and obtaining regularity results is challenging, although there are some papers on this topic. So yes, there are some references. For example, Dylan Posamai and co-authors. So the new MFC problem is not standard. Here, the presentation was based on my papers with René Carmona, but the same techniques have been used also by other people, including Jean-Pierre Fouque and one of his students on mean field control with delay. Maximilien Germain has worked a lot on deep learning for optimal control and also Makin-Vlasov control. And we also used a similar technique in these papers that I already cited, where we do an application. So I will come back to this actually a bit later. And here you can also use a similar method for ODEs. So if you have a forward-backward ODE system instead of a forward-backward SDE system, you can still use the same method, try to learn the solution starting from an initial condition. And so you can find, and so here we use this approach for graph-on games. And the main challenge in graph-on games is that you have a different index for every player. So it becomes an infinite system of ODEs, or if you want an ODE parameterized by one extra parameter. And so using neural networks was convenient, even though probably not required because it's not very high dimensional, but it worked quite well on this example. So two examples of extensions to finish on this, just to show that actually in these methods, there is a lot of flexibility. So I think that's one advantage of these deep learning methods with some effort, but not a huge amount of effort. You can adapt them to various settings, and they tend to work well, provided you tune the hyperparameters adequately. So this takes some time and some effort to find good values for hyperparameters. But yes, you can solve other types of problems, at least empirically. And again, some aspects of the convergence questions have been addressed, but most of the time, there are still many open questions. So if you're interested in these methods, there is a lot of work for mathematicians, I think. So first example is solving Stackelberg game. So I will not give a very long description, but briefly, the idea of Stackelberg infield game is that you have a principal who chooses a policy. This policy influences the agents who solve a Nash equilibrium. So the Nash equilibrium that you get depends on this policy. And then the principal has a cost which depends on the Nash equilibrium. So you can think of, for example, a government during an epidemic, and the government wants to decide what policy should be used in terms of social distancing and masks and lockdowns, as we have seen during the COVID pandemic, for example. So the government takes some decisions. Of course, the government cannot control perfectly the agents. So maybe you announce what the policy, what the rule is, and what is the penalty for not following the rule. And so here, this is represented by this parameter lambda. So you see, this is the cost for a mean field game. Alpha is the control for a single agent. Mu is the mean field. So I can do the same thing looking for a fixed point. But there is this lambda which influences the Nash equilibrium I am going to find. So the Nash equilibrium will be some alpha hat and some mu hat, but they are both depending on the choice of lambda imposed by the government or given by the government. But then the government pays a cost or has a cost, maybe an artificial cost, maybe a moral cost. For example, the number of people infected or the number of deaths. and the government wants to minimize that. So you cannot control people, you cannot force people to stay inside. Well, sometimes you can, maybe with a hard lockdown. But if you are in a situation where you want a smooth control, maybe incentives rather than hard control. So if you want to incentivize people to behave in a certain way, then this is really like a Stackelberg mean field game. So this type of games has probably applications in many settings. And so Stackelberg games without mean field are not new. And in fact, it has been studied a lot in the literature on contract theory, in particular by Sannikov and Zviternich and Dylan Posamai and co-authors, and more recently in the context of mean field games by Carmona Wang and Romuald Daly and co-authors. These were the first papers, and since then there are more and more papers on this topic. So what is the idea? What is the connection with what I presented before? Well, the idea is that these approaches, or at least one possible approach to solve a Stackelberg mean field game is to rewrite the Nash equilibrium as Makin-Vlasov FBSDE. So this is standard. This is what we already discussed. You can use, for example, Pontryagin maximum principle, or you can represent the value function. In fact, usually for this approach, we use the value function of one representative agent. So y is equal, yt is equal to u of t and xt. And then you combine, so there is a terminal condition for yt, and in some specific settings, under some assumptions, you manage to combine this penalty with the principal's cost, so the cost for the government, let's say, or the regulator, and you obtain a single optimization problem. So the result of this is that you have a single, in fact, MFC problem. So it's a mean field control problem, which characterizes the solution to the whole problem for the principal and for the Nash equilibrium. In principle, it's a bi-level problem, 2 levels, but you manage to write everything with a single mean field control problem. So this is discussed, for example, in this paper of Romuald Daly et al. But then once you see that, well, you say, so now we can apply the method discussed previously because it is an MFC problem. So we can parameterize the control, whatever it is, we can parameterize the control by a neural network and run stochastic gradient descent. That's the idea. I'm not saying it always works. We did experiments in some cases, but and we looked at the theory also in this paper in some cases. But for sure, for the general case, there is still work to be done. So here, for this type of game, you can find the code of Gokce on her website. There is also a connection. The last paper I mentioned here is a work we did with Sébastien Baudlet and Brieux Freinet, Amal, who is in the audience, I think, and Yuchen, who I already mentioned, who worked during SMRAX on mean field optimal transport. So this is an MFC problem, except that instead of having a terminal cost, you replace that by a terminal constraint on m at time t. So this is really an optimal transport problem because m0 is given, m at time capital T is given. You have to match it, but you have mean field interactions in the dynamics. For example, congestion or other mean field effects. So it's not a standard optimal transport problem. And so one of the approaches on which Sébastien and Brieux work is to use the direct approach that I mentioned earlier, transforming this as a penalty, a terminal cost. And then once you have a penalty, you are back to a standard MFC problem, and you can apply the same method as I described before. So no FBSDEs here, but just this direct approach. So again, the bottom line is that if you have a problem and you manage to transform it into an optimal control problem or a mean field control problem, then you can apply the direct approach I have mentioned at the beginning. Parameterize the control by a neural network, run stochastic gradient descent. It's very straightforward, and there are other methods than that, but this one is quite convenient to implement. Okay, another example, but actually I will discuss it in the next slide deck in more detail. But the idea was the following. So as I just said, there are other algorithms, and one of them consists in using dynamic programming instead of optimizing over the whole time horizon. Because in the direct approach, you optimize over the whole time horizon. So you parameterize your control, and then you tune it to minimize the cost on the whole time horizon. But you know that optimal control, in general, you have dynamic programming. So why not using dynamic programming and then doing backward induction, starting from the terminal time and training the neural network backward in time? So that's the idea behind the so-called DBDP method introduced by Pham and co-authors. How can we use that in the context of mean-field control? So here I rewrite the mean-field control problem, but it's not directly amenable to dynamic programming equation, because here we think of the state as X. But actually, if you want to do dynamic programming, you need to put M in the state. So if you want more details on dynamic programming, here are a few references. And so every time you end up with a value function, which is going to be a function of basically T and M, because you need the starting distribution, you need the distribution at time T in order to be able to restart the problem from time T, right? If you want to restart the mean-field control problem from time T, and I only tell you the state of X, well, you don't know what the distribution is, so you will not be able to predict your future costs, right? So if you want to compute the cost, you need to know the current distribution at time T. All right, so mathematically it works, beautiful, but then how do you do numerically? Because if you want to use this dynamic programming approach, it means that we should replace V by a neural network and we should train it backward in time. But the problem is V is a function of a distribution. So if you are on a continuous space, it's not clear how you represent the distribution. So before addressing this question, let me just write the DBDP for non-mean-field control. So this is in the paper of Urey et al. So in fact, there are several versions, but one version consists in looking at the BSDE and trying to train, Y as a function of X and Z as a function of X here, given the next Y. So imagine you start from the terminal time, then you know exactly what Y should be at terminal time. And you go one step backward and you try to find Y at the previous time step. And if you discretize the BSDE, which basically amounts to following the Bellman principle, but one step backward, you end up with a term of this form, and you try to minimize it. So when you minimize it, it means you are trying to choose Y and you are trying to choose Z so that this quantity is as small as possible. Probably it's not going to be zero because here there is an error due to time discretization. You see delta T, so there is some kind of incompressible error. But if delta T is very small, you should be able to make this loss very small as well. Version 2, instead of training a neural network for Z, you use your knowledge that Z should be the derivative of Y up to the constant sigma, right? So yesterday someone asked this question, or the day before maybe, someone asked the question, what is Z? So one answer is Z is here to make Y adapted. So here you can check the paper of Pardue and Peng on BSDEs. But another answer is to say Z seen as a function of X, so Z at time T seen as a function of X should be the derivative with respect to X of Y seen as a function of X. And the idea is that Y represents U and Z represents the gradient of U. So since we know that, it means we don't really need to train an extra neural network for Z because we know that Z should be exactly the gradient of Y, right? So here we reduce a little bit the complexity, which may or may not be an advantage. So in some sense here, you have to train two neural networks, right? So here you train two neural networks, Y and Zn. Here you train only one neural network and you compute its derivative here. So it's smarter for sure, but sometimes over parameterizing is helpful. in deep learning. So sometimes having too many parameters, and for example, 2 neural networks instead of 1 is helpful. So this is hard to predict. And so here the authors have implemented both methods. So for also for more details, there is this review paper of Maximilien Germain and Nguyen Pham and Xavier Varin on this method and several other methods. So in the case of MFC, we cannot, as I said, we cannot directly take the distribution and represent it in a computer as it is. We have to do some approximation. So what we did with Maximilien and Nguyen and Xavier was to use an empirical distribution or an empirical set of particles, again, x1 to xn, but then using a neural network which is symmetric with respect to the input. So here the idea is I take n particles, I give them as an input to my neural network, but I know that the neural network should be a function of the distribution and not really a function of x1 of the vector somehow, because the order does not matter. So there are some architectures which are designed specifically for this. The function is symmetric with respect to the inputs, and this actually has applications in computer vision, for example, because you have clouds of points and you want to recognize the shape, and you don't really care about which point is has which index, you just care about the shape. Okay, so I will give more details in lecture 5. I give a few more references, and if you are not happy with just particle approximation, there are other ways to approximate the distribution. We tried some of them with Gokce and Jia Cheng with a postdoc at Berkeley. But certainly there is a lot more to explore. All right, conclusion. So I presented 2 algorithms based on the stochastic approach, a direct approach, what I call direct approach, and I will refer to it in this way in the following, without any optimality condition. So you just take your control problem or mean field control problem, and you replace the control by a neural network, right? So let me rewrite this. You have J of alpha, and you approximate it by J of phi theta, where phi theta is a neural network, and phi theta, you are, so, okay, and then instead of writing the inf over alpha of J alpha, you write the inf over theta of J theta, or if you want J tilde, it's not the same function, but it's a function of the parameters. So this is finite dimensional, and now you have a finite dimensional optimization problem to solve. You could use something else than neural network. So someone suggested wavelets or other approximations, and why not? Somehow for this method, you don't have to use neural networks. It turns out that neural networks work well in high dimension, at least after some tuning, but there are other classes of parameterized functions. DBSDE, the idea, at least from my point of view, is to rewrite the FBSD as a control problem and then apply the previous method. Extensions, yes, I stress in red many open questions, so I know that I'm giving a talk mostly to mathematicians, so I apologize for not giving a lot of mathematical results in terms of numerical analysis. I'm hinting at some results and giving some references. If you want more, just let me know. But anyway, not so much is known for these deep learning methods. The same will be true later for the lecture 5 and 6. But these methods seem to work very well in high dimension, and so there are a lot of intriguing properties to investigate. And a few more references. So I think I will stop here for this lecture and move on to the next one, unless you have some questions right now. Maybe it's a good time if you want to ask some questions on this lecture. All right, so we have one question. Thank you. So how does DP solver compare to global DBSD? Yes, one in terms of efficiency. So yes, thanks for the question. I think my understanding is that maybe, okay, let me try to answer. My understanding is that you want to compare what I call the direct approach here. So what I've described here, where you directly parameterize the control, and the deep BSD, the deep DB, sorry, DBDP, deep backward dynamic programming of Pham et al., where the idea is basically you start from the terminal time. Here you know that the value function should be exactly equal to G. There is no control to train. And then you go backward in time. And here you train V, or if you want, you could train alpha also. In some of their papers, train alpha. So you train alpha at time capital T minus delta T. And then you go one step backward. You train alpha at time T minus 2 delta T. And then you keep going backward. Okay. So let me answer for, yes, the dynamic programming method. So I think it is this one. This one is a dynamic programming approach where you go backward in time. And so I think there are advantages and drawbacks in both. If you check the papers of Nguyen Pham and co-authors, they have some cases where their method succeeds, whereas the global approach, global in time, where you train over the whole time horizon, fails to converge. For example, it is stuck in some bad local minimum. And there are some reasons behind this. So it's true that starting from terminal time means that you train over a small time horizon at each iteration. And so it's an easy problem. And furthermore, when you move to the previous time step, here, you can initialize the neural network using the next time step. So you already know the control of the value at the next time step, and you can use that as an initial guess, and then usually it converges very quickly. So you can go backward in time in a quite efficient way. Of course, one drawback is that if you make an error, if here your neural network is not trained very well, then you are going to accumulate the errors and you will never be able to correct it, right? Because you don't reevaluate. I mean, except if you retrain the further network, so that's also a possibility that has been tried in some works. But if you use complete like backward dynamic programming and you train only one time step at each iteration, then you may have accumulation of errors backward in time. Another thing to keep in mind, I think, is if I go back, so I skipped this detail, but it's a very good question. So here, what I didn't write is what is the expectation over? The expectation is over xn, because I need to choose xn, and then it's over the delta w n plus 1. Okay, so you give me xn, which is the starting point at time n. You give me a Brownian motion increment, and I can compute this quantity if I have the neural network for y and for z. Here, one question is, where do I sample xn, right? Because, I mean, in principle, the whole space, but it's not really feasible. So I have to choose a region, or maybe a Gaussian density centered somewhere, and with some variance, where I'm going to sample xn. But this means that these neural networks for yn and for zn will be trained in the region where I sample xn, right? But the point is, I don't know where xn should be sampled, because this is going to depend on the trajectory starting from time 0. So intuitively, when I start from time 0 at x0, then maybe the trajectories are going to go up most of the time, because my control is going to bring me up, right? But so when I am at time here, at time m, I should sample here, because these are the points that are going to matter when I'm going to use my control, right? So I would like the neural networks to be trained very well in this region, but I don't know this region in advance, because I would need to have solved the problem here, which is not the case because I'm going backward in time, right? So here there is really a question of sampling. And of course, what you can do is you can train backward in time, and then when you arrive at time 0, then you simulate trajectories and you improve the neural networks. But this is more complicated than what I'm describing here, which is the plain version when you just go backward in time. This version has really this question of solving the points, important points. And so this question does not arise in the direct method, because in the direct method, you really simulate a trajectory starting from time 0 on the whole time horizon using your current control, right? So every time you simulate the trajectory, you get a cost along the trajectory really generated using your SDE or discretized SDE. What is the interpretation of a parameter in the state equation in the model of interbank? Thank you. So for this, the short answer is you can check the paper of Carmona et al. Because they have explanation, but let me see. So here, yes, the a parameter is this one. I don't remember the exact interpretation, but basically it says somehow how much you want to borrow or lend with other people, with other banks. So if you set A is equal to 0, it means that you are never borrowing or lending to other people because you never have this mean reverting term in the dynamics. On the other hand, if you take A very large, it means that as soon as you are a little bit above or a little bit below the mean, you borrow or you lend to other banks. When I say borrow or lend, don't take it very literally, because okay, maybe you borrow money, but you never give it back. So it's not really borrowing, right? In this model, we don't keep track of who is taking from who and giving to who, right? So I'm saying borrowing and lending, but you don't really give back money to the same bank from which you have borrowed, right? So in this sense, it's not very realistic, but that's what is happening in this model. Okay, so maybe we can move on to the next. Actually, I can still share my slides, and I will open this one. Okay, so lecture 5. Now we turn our attention to PDEs, and so forward-backward PDEs, and also the master equations that I haven't discussed too much. And I will not discuss too much the theory here, but I will briefly talk about numerical methods or some first developments, because there is still a lot of work to do in this direction. And I think it's a promising direction for applications as well. So I will try to motivate that. Mainly two sections. Meaningful game PDEs in the sense PDE system, forward, backward, or the ergodic version, but the counterpart to this, and using the so-called deep Galerkin method introduced by Sirignano and Spiliopoulos. And the next point is about the master equation. So I will present two methods, one for finite state master equation and the other one for continuous space. In fact, the one for continuous space is the one I just discussed now. So I will give a little bit more details using this backward approach with symmetric neural networks. So a recap of lecture 4. Here I can go quickly because we just did it. Now the goal is to look at FBSDs. As far as I know, so this is for FBSDs. The goal for today is to discuss PDEs. And as far as I know, there is not a very comprehensive comparison. So yesterday I had this question. Thank you, Abdu, for asking. As far as I know, there is no very thorough and extensive comparison between these methods. So, for example, some of the papers, so the papers that introduced the DBSD method by Weinan He and Jieshun Han, Arnulf Jensen, the title is solving PDEs in high dimension. So it's true, it is solving a PDE, but in a certain sense, by using the BSD, right? But how does this compare with the DGM method? in particular I'm thinking about Mifflin game problem. Maybe this has been done for non-Mifflin problems. I suspect some people have looked at that. But for Mifflin games, I'm not aware of like a very careful comparison and which method is best in which case. For sure, they each have advantages and drawbacks. For example, the DGM method can easily be used in the ergodic setting, whereas if you try to use FBSDs in the ergodic setting, it's not so simple. But yes, so if you are interested in doing experiments, it's probably an interesting direction. So here I will focus on methods for PDEs. I will start with ODEs, actually, just to give the intuition. So let's consider an ODE. And in this ODE, I have, so the unknown function is phi here. And you see that there are two terms, there are two components in the ODE. There is a term which is for every x. If you want, you can interpret this as time, maybe. But you have x between a and b, and you have more or less an initial condition if you want at t is equal to a, for example, or x is equal to a, to follow the notations I'm using here. So you have a condition here, a boundary condition. You have the ODE inside. I'm using some abstract form for the operators, but I'm going to take a concrete example very soon. And you want to solve this ODE. And the question is, how can we do that using deep learning? So in principle, this has nothing to do with neural networks. It's not stochastic, so it's not very clear how we are going to use SGD, right? If you want to use stochastic gradient descent, well, it's not very clear because here it's not a BSDE or an SDE, so nothing stochastic. The first step is to say, well, my solution between, so here I have the interval A and B, and my solution takes some value here, and then it evolves, and I'm going to try to approximate it using a neural network. So the neural network here is going to be a function phi parameterized by theta, and we will see it as a function of x, taking values in, let's say, R here. You can take a multi-valued ODE if you want. So this function has a derivative. So phi prime theta is equal to the gradient, or just the derivative. I will write it like this, partial x phi theta. And the reason why I use a partial x notation is because I can view phi also as a function of theta and sorry, so here this is a function from R to R, and here I can do R to R, and it's a function that I can write like this. I can view it as a function of two variables, or I can view it as a function of one variable. So during stochastic gradient descent, I need to compute the gradient of phi theta x with respect to theta. But in an ODE, here I need to compute the derivative with respect to x. Okay, because this is the derivative with respect to the real input somehow. The other one is more like a parameter. But in some sense, from the point of view of TensorFlow, we can do both because the neural network is completely implemented. So let's take a concrete example. Let's imagine that phi theta x is equal to, maybe I take x, I multiply by W1, and I add a bias B1. I use some maybe sigmoid activation function. I multiply by W2, and I add a bias B2. So here, theta is equal to W1, B1, W2, B2, which is in dimension 4, let's say. Well, in fact, it has to be in dimension 4 because, no, actually it could be in higher dimension if I want. I could take W1, I could take B1 to be a vector, and then W2 would be the projection to R. But anyway, let's imagine it's in dimension 4. Then I can compute the derivatives. So if you look at this formula, I'm sure that you can compute by hand the derivative with respect to B1, for example, or phi theta x, right? And you can compute by hand the derivative with respect to each of the parameters. So you could really compute this gradient and you could implement gradient descent by hand. You can also compute this one, partial x of phi theta, right? You can do it by hand, at least if you have a formula for sigma, but sigma is, for example, the logistic function or some well-known function for which you have a derivative at hand. But this would be cumbersome if you use a deep network, right? Computing by hand the derivative. So in fact, TensorFlow, PyTorch, and other libraries can do that for you. So you just need to say, I want the gradient, and they compute the gradient for you, and very quickly, even for deep networks. So this is the idea behind using a neural network here, but there is one question. The next question is, well, how do we train this neural network, right? So now the goal is to find, so the goal is to find the value for theta in the set of parameters. So usually it will be R to some power. The power is a number of parameters, for example, R4, such that this holds, or maybe this holds approximately, because maybe you cannot make it exactly equal to 0. You have some approximation error. So how do we find this value of theta, right? Yesterday I said, or one of the most popular methods is stochastic gradient descent. Can we use stochastic gradient descent here? If we want to use SGD, well, we need to sample points. Okay, so actually there is a way to rewrite this as a stochastic optimization problem, or an optimization problem with an expectation. So if you remember yesterday, I started the presentation with neural networks, on neural networks, with a loss that contains an expectation. So let me write this loss as an expectation. I mean, let me recast this problem as the loss with an expectation. And so you want to be perfect everywhere. So in fact, what I can write is the integral between A and B of this operator, f of x phi theta x, maybe the first order derivative because it's an ODE, maybe higher order derivative. And I want this squared dx to be equal to 0, right? I'm really writing the squared residual for this ODE, in fact. And then I interpret the integral as an expectation where I take a uniform random variable between A and B. So this is really equivalent. It's just a rewriting. I also have the terminal, or rather, sorry, the initial condition here, or the condition at one of the two boundaries. And now I can use stochastic gradient descent. I'm going to sample points X, evaluate the function capital F, see if it is 0. If it is not 0, then I tune a bit the parameters, I pick another point and try again. And by picking many points, I'm hoping, and running stochastic gradient descent in this way, I'm hoping that in the end, it will converge to a minimizer. And hopefully the minimizer will be close to 0 if my class of neural networks is rich enough. I hope this makes sense. Any questions here? All right. So we use SGD, and the key point here, I mean, I think the main highlight is that we can solve an ODE without discretizing time at all, right? So here there is no time discretization. So one nice consequence is that after you have trained, so you use SGD, you are going to get some parameter, maybe theta star. Maybe it's not exactly the optimum, but a local optimum. You get theta star, and then you can evaluate phi theta star at any x, for any x between A and B. In fact, even outside A and B, it's still defined. So you can really evaluate the function everywhere. So we can claim that we have solved the ODE on the whole interval, right? Whereas when you discretize time, well, there is always a question of what happens between the time steps. So you can interpolate, etc. But Here we don't need any discretization. And this will be an advantage in high dimension because discretizing high dimensional spaces means that you need a tremendous number of points, at least if you use a uniform grid. And so the hope is that using neural network in this way for not just high dimensional ODEs, but even PDEs will help us because we don't need to discretize at all the space. Here is an application. I take a specific ODE in dimension 1 between 0 and 5. The operator capital F is just this, or the function rather is just this. And I take an initial condition equal to 1. It turns out that this ODE has an explicit solution, which is x minus 1 plus 2 to the exponential minus x. It doesn't matter. I just want an ODE where I have a solution that I know to check if the algorithm is converging. Because again, when we run FGD, typically you are going to see something like this, and then you are wondering whether the algorithm has converged or not. Maybe later it will keep decreasing to a lower level. So sometimes you need to wait a really long time. And even if it goes to this level, has it converged to the true solution or not? It's not clear. It could be that you made a mistake in your loss function. It could be that you made a mistake somewhere, or just you didn't make any mistake, but for some reason, the loss function is not really characterizing the solution. And then the neural network minimizes the loss, but maybe what you get is not really the solution to your original problem. So that's why it's important to be really careful. If you just look at how the loss behaves, it's very easy to believe you have solved the problem while you didn't. So the loss, I would say in general, the loss is not a sufficient indicator. It's really important to have some side information about the problem you try to solve. So of course, knowing the solution is a very strong side information. Okay, it's too much, but it's just for illustration. But in general, when you try to solve a problem, you have some information about the shape of the solution. Maybe you know that it should be convex, concave, increasing, decreasing, or some behavior in some region. And then you can check whether what you get makes sense or not. Maybe you can estimate a priori the value at some points, and you can check that it agrees, etc. And the neural network helps you to solve on the whole domain, for example. Okay, so what we see is this. I will show the code just next, but let me show the figures first. So at the beginning, the neural network is basically flat, and in red, you see the solutions that should be matched. When I write time here, what I mean by time is actually x between 0 and 5, but I have in mind an ODE where x is like time. So you see at time 0, even the initial condition is not satisfied. Right? The neural network does not satisfy the initial condition, and it does not satisfy the rest of the ODE. Then you start training. And at the beginning, the neural network does something like this. So you see it catches roughly the slope, but it's still not very good. And then little by little, so it's not just one iteration. Okay, here it's like 700 iterations. But little by little, it's going to learn how to bend and how to match very well the solution. It's not trying to match the solution, okay? It's trying to solve the ODE. It's trying to minimize the residual of the ODE. And the way we check that it works is by looking at the solution. So I'm not telling to the neural network, try to match this function. This would be too easy, right? If I just write phi theta of x minus the solution, which is x minus 1 plus 2e minus x, this would be a bit trivial because I'm just basically fitting. I mean, it can be useful in some situations, but that's not what I'm doing here. I would be just fitting the solution using a neural network, okay? But what we are doing here is not this, it's trying to minimize the residual of the ODE, and as a consequence, the neural network becomes close to the true solution. Okay, so, and you see that at the end, the terminal condition is matched, but actually it takes a while, right? So maybe it's not very intuitive, but the neural network, for example, here, the neural network is Okay, it's not perfect, but it's not so bad, particularly in this region. But here it doesn't have the correct initial condition, right? So you may say, well, let's try to impose the initial condition very strongly. And how would you impose or incentivize the initial condition? If I go back, what you would do is here, you can put a very large constant. And if you do that, then the loss function will give a lot of weight to the initial condition and less weight to the residual. So you can hope that the neural network is going to learn very quickly the boundary condition.
Mathieu,
However,
there
it's
is
not clear that, yeah.
Question. There is an immediate question.
Yes, thank you. Can we add some regularization term in the loss? Yes, absolutely. You can add some regularization terms, and sometimes it helps. So, for example, typically you can add some terms like in lasso or ridge regression, and this is used also in these methods to regularize the output of the solution. I mean, the output of the neural network. Yes, thanks for asking. Okay, so let me show you this sample code just to make things concrete. Okay, so I think it should be this one. Yes, so it's inspired by the DGM method, but really there is nothing complicated here. So it's not really, I think the DGM method is really for PDEs. Here it's just for an ODE. All right, here actually I didn't put any sections. Sorry, it's just a few lines of code. You see, not even 100 lines of code. So if you are not familiar with deep learning, maybe this is a good starting point because this code is pretty short, and probably you are familiar with ODEs. So the goal is kind of clear, maybe more than when you do stochastic optimal control or FBSDs. So what is the sampling? The sampling is a point in time. So here I call the interval time, which was X in the slides. You sample a point in time, then you define the loss function, which is a function of the neural network and the sample, right? So you remember my function L, which is a function of phi theta and the function of xi, let's say, the sample. It's exactly this loss function. Here there is one line which says, I'm going to compute a gradient. So I tell the neural network, evaluate, so compute the neural network output at this point in time. This gives me the value. And then I call this tape.gradient, which computes the gradient of the neural network. And here you see, I say tape.watch time sample, meaning that I'm going to compute the gradient with respect to the input X or T. So it's not a gradient with respect to the parameters, it's a gradient with respect to the other input, which is the real input of the function somehow. So why do I need this D1NN? Because that's what I need in my ODE. So then I do D1NN, it's like phi prime, and I look at the right-hand side of the ODE. Okay, I square this, and this is the loss for the ODE, but I need to add the loss for the initial condition, which is just the neural network at time 0 should be equal to y0, which is a value predefined here, y0 is equal to 1. The total loss is a sum, but I could put a coefficient in front of loss in it. I'm going to show that. You do one step of gradient. So here you need to compute the gradient again, but now with respect to the trainable variables, which are the parameters theta. Okay, so trainable variables are theta. I compute the gradient with respect to theta in order to do one gradient step. This is the gradient of the loss, by the way. So you see the loss involves all of that. So, and it can be even more complicated. So computing this gradient could be painful if I had to do it by hand, but here it's done in one line of code and quite efficiently. Apply gradient means that I update the neural network based on the gradients. Then you train, and training is basically just iterating one step of gradient. The rest is just for plotting. The neural network here has 200 neurons on 2 layers, sigmoid activation function, and then a last layer, which is of dimension xdim. Here, xdim is just 1 because I take a one-dimensional ODE. The other hyperparameters, here you see the learning rate. So I use Adam optimizer. Learning rate here 10 to the minus 3, number of SGD steps, and train is the number of points in one mini batch. So actually, when I do one step of gradient descent, I don't do it with just one sample, I do it with 20 samples. So on 20 samples, you compute the neural network output, you evaluate if the ODE is satisfied or not, and then you compute the gradient of this loss, which is an average over the 20 points. So this will be more precise than doing gradient descent for just one step at a time, 1 point at a time. And the validation is I sample 100 points and I evaluate the residual at these 100 points every iteration or every 10 iterations, for example, to check how it is behaving, not just on the 20 points. So I sample new 20 points at each iteration. Okay, so actually during training, the neural network is going to see a lot of points. It's going to see 3,000 times 20 points. Right, so if you're on an interval, it means really a lot of points. But each time you see 20 points, you do just one gradient step. So you don't try to solve the full problem, just one gradient step. And then you pick another 20 points, and then another 20 points, etc. So here is what you get. I'm not going to run it again. This is exactly, I think, the plot I showed in the slides. And you see that it matches after a while. So let's see, maybe around, okay, around maybe 1,500, 1,600 iterations, it's already pretty good, right? So again, the red line is the solution of the ODE, the exact solution, and the blue line is the output of the neural network on various points on the interval 0, 5. Okay, so let's play a little bit. I just want to show what happens, for example, what happens if I comment this line and I replace it. So for the last layer, I replace it. So I want to show that because these are mistakes that I made, or at least experiments that I made, but not always on purpose. So what happens if on the last layer, you put a sigmoid activation function? Okay, there is a sigmoid activation function on this layer, why not on the last layer? So let's see, I need to reconnect. So let's see, sorry, it's going to take just not so long. And now it is running. So same architecture, you see the number of parameters is pretty large, 40,800 parameters. So basically we are doing gradient descent in dimension 40,800, right? So it's pretty large. So here you see that, okay, with a sigmoid activation function, first of all, the evolution is different. It manages to match this condition, but then beyond that, it doesn't do too much, right? It seems that now it's stuck here. I say it seems because we would have to wait forever to see if at some point it's unstuck. But if you look at the loss, so here I'm not plotting the loss, but if you look at the loss at the beginning, it's 6.3, then 4.37, 4.37, etc. So if you just look at the loss, and if you didn't know this solution in red, you may believe that the algorithm has converged, right? Because the loss starts at a high level, it goes down, and then it remains at this level, and you could say, well, wonderful, the algorithm has converged, right? Because it's not decreasing anymore. Well, but the thing is, now here you know the solution, and you know that the algorithm has not converged, at least not to the correct solution. Maybe it has converged to something, but it's not the correct solution. So why is that? Maybe you have some idea. So this is the output of the neural network, and the last layer has a sigmoid activation function, which is a function that takes value between 0 and 1. So in fact, the neural network will never be able to output anything outside 0 and 1. So here, it turns out that the neural network decides to stay constant equal to 1, because this is what is going to minimize the loss among this class of neural network, right? For this given architecture with this constraint on the last layer. So I don't know why this is a minimizer, but apparently this is a minimizer among this class of functions, right? So there is a question, have we an estimation of the number of iterations to converge? So no, I don't have an estimation of the number of iterations. It's a very good question. So this is what I would call the optimization error. So if you remember yesterday in the at the beginning when we started on deep learning, there is the approximation error, which is the class of functions. So here you see that because of this sigmoid function, which is a bad choice, of course, on the last layer, but the approximation error is very large, and I think that's the reason here. Then there is the estimation error related to the number of samples, and the optimization error related to the number of steps in the algorithm. And for these two, I think for the second one, we have some arguments related to statistical learning. And for the last one, I think it's pretty difficult to obtain rates of convergence. You can have asymptotic, you can have results of asymptotic convergence, but what you are asking here is a non-asymptotic bound on the number of iterations. And this is difficult, I think. I'm not saying there is absolutely no result, maybe in some settings, like maybe single layer neural network, etc. But for deep networks, it's really not trivial. And moreover, even if we had such a bound, here you see that I would say the algorithm converges. There is no problem with the algorithm. SGD converges, but it converges in your restricted class of neural networks, right? So you have a restricted class because you put, I put a sigmoid activation function on the last layer, but you could take a different architecture, and still this architecture has some limitation, and so the approximation error is big here. How do we know the best activation function to use? A great question as well. I don't think there is a perfect answer in general. So there are some guidelines about the activation functions. What I'm saying here is really for the last layer. So I think the last layer, usually it will depend on your problem. For example, here, I want a solution, and in principle, it can take any real value. So I shouldn't put any activation function on the last layer, at least not an activation function that has a bounded image. Now, if I know that the function I try to approximate has an image in a compact set, then maybe it's a good idea to use a sigmoid activation function, maybe reshaped a little bit or to increase the range. And then I will always have outputs in this range, and this might be a good idea. So for the last layer, you can really use the knowledge of the function you try to approximate. Not a lot of knowledge, but just the range, for example. And for the inner layers, it's more complicated. I think it's really experimental in most cases. So if you have a problem, just try a bunch of activation functions one by one and see what works best. I don't have a much better guideline. I know it's frustrating, but I think in many cases, that's it. Now, what I'm saying here is a bit oversimplifying. There are some heuristics, maybe. So there are some activation functions that work better for some architectures, etc. So, but then it becomes specific. So you don't have to try everything in the world. There are some heuristics to choose the activation function, but I think no real rigorous proof for a very general case of which activation function is the best. Because again, I think the problem is not so much the approximation. So there is a question of the approximation class, but here you have universal approximation theorem. So in some sense, you are going to have a good approximation error, but then the training is really complicated. So depending on the architecture you choose and the activation functions you choose, sometimes the training doesn't go well. Like the gradient is going to vanish, the gradient is going to explode, and these kind of things, which is not related to the approximation error. Okay, one more question. By simulation, how do we know that the method reaches the exact solution? So that's a very good point. I think in general, we don't know that we have found the exact solution because otherwise it means we already have the exact solution. There might be some problems for which it's hard to find the solution, but it's easy to check that you have the solution. But in general, you really don't know. So you just run SGD. You see how much the loss is minimized, you try different hyperparameters, and you take the set of hyperparameters that gives you the smallest loss after training. And then you hope that this is close to the true optimum. Yeah, so all the examples I'm showing here are really, for illustration because I have a benchmark solution, right? But But then I can show you that the method works or doesn't work in some cases on this benchmark example. So at least you can convince yourself that the algorithm is implemented correctly. I think that's a good first step. Then you know the algorithm works, at least in these cases. And then you can use the algorithm in some cases where you don't have the solution. All right, more questions. So if we have only noisy data, what is the form of the loss function we should use? We should calculate the order between what and what. So here, I'm not sure which example you have in mind, but okay, so maybe, yes, I think I understand your question. So here it's true that, let's see. Well, not really here. I don't have noise in the data. So, okay, if you are trying to do a regression problem, for example, then it makes sense to say I have noise or classification. Then you can say I have noise in my labels. But then this is for supervised learning. Here, in some sense, the question does not arise because you have you sample points in the domain. So in some sense, you have randomness, but it's not noise, right? So here I don't have any data in the classical sense. Now, if you have a specific model, we can take a look. And another question. So thanks a lot, everyone, for asking questions. It's really nice to have interactions. So to follow up on the last question, is there any hint that we are in a transient plateau before the fall towards the best conversion state? So unfortunately, not really, I think. At least not by just looking at the loss, because if you look at the loss, you have a plateau and you really don't know if you are somehow at the minimizer, or at least very close to the true minimizer, or if you are just stuck in a bad local minimum, and then the neural network is going to find a better way. So for this, I'm not sure. Maybe in some specific cases you can have some hints. For example, again, if you have some side information. So I had some cases where I was trying to train a neural network, and I knew that the function should be, let's say, strictly convex. And then at some point, the neural network was learning. So the loss was very flat at some point, but the neural network was constant, for example. Then I knew that this couldn't be the solution because it had to be strictly convex with some growth towards infinity. So you see, in that case, I don't know the solution, but I know some information about the shape, like it should grow to infinity at infinity. If I see that the neural network is giving something constant, then clearly it's not the solution, right? So sometimes you have some ways to check, but then there is a regime where everything is checked, everything looks reasonable, and you don't know if you are in a plateau or not. So this happens in deep learning indeed. But this is a general problem with deep learning, not specific to mean field games, I think. All right, so thanks a lot for all the questions. Let me go back to the slides, and maybe very soon we can take a short break. So, okay. Okay, so, oops. So again, you can download the code. They are here just for the sake of illustration. So feel free to play with them, improve them, send me some comments, feedbacks. If you find some mistakes or if you find some ways to improve this code, I would be very happy to hear back. Okay, so maybe, let's see. Yes, how about we take a short break now and then we resume. So what I will do after the break is solving a mean field game PDE system using this DGM approach, solving an example of master equation for finite state mean field games using the DGM method again, and then revisiting the approach I gave at the end of lecture 5 with just a little bit more details on the DBDP approach for mean field control, master equation or Bellman equation, which is in principle infinite dimensional. If there are further questions, maybe you can post them in the chat.
Yeah,
okay, thank
Mathieu,
you. Yeah.
Only one suggestion that you post the links
Okay.
for the collab notebooks.
Yes, it's a good idea. So let me do that maybe during the break. I can send the link to the collab notebooks. Thanks. Okay. Good idea. Okay, yes. And the link, yes. Okay, sure. I will do that during the break. And if you have further questions, feel free to post them in the chat and I can address them when we resume.
Okay. It's 11:30. Would you like to take 10 minutes, 15?
Up to you. We can take 10
What do-
minutes if you want. Maybe we take 10 minutes
It's
and
up to you. It's up to
yes.
you. We are only listening and you are talking. So
Okay, let's do
okay.
10 minutes. So it will give me to recover all the collabs links and send them in the chat. And yes, we can resume at 11:40, maybe France time, and
40.
12:40 and 10:40, I guess, Morocco time. Is it correct?
Okay. Yeah. If you have any slide, you would let still the pause.
Okay.
It will be nice. Okay.
I'm not sure which one
Thank
is
you,
best.
Mathieu.
Which one do you want to see? Okay, I don't know. I can show. Okay,
The
maybe I can show.
financial model.
Yes, if you want this one
Or any
okay.
you would like.
Okay, I guess I will just I don't know if there is a best slide for this, but okay, I will maybe leave it to just to here, and then we can resume, I guess.
Thank you.
Thank you very much. Okay, shall we restart? Is it a good time to restart?
Okay, Mathieu, thank you.
Okay.
Please go on.
Okay, thank you very much.
There are no questions. So.
No questions, yes, for now.
Okay.
All right. So what I would like to show now is how to use very similar ideas to solve the PDE system in a mini-field game. In fact, there are several forms of PDE systems. So let me restart from the method introduced by Sirignano and Spiliopoulos. So the idea is now that you have a PDE. So X is multi-dimensional, and you have partial derivatives. So here, this D represents the gradient, so all the partial derivatives. And for example, it would contain the partial derivative with respect to time if you imagine that X is replaced by T comma X. So the X here could be interpreted as time and then really the state X. So in this case, you would have the time derivative here, and the second order derivative could encode the Laplacian if you need it in your PDE. You could have boundary conditions as well here on this bounded domain. So I write things in a very general way, but in principle, the method can be applied to very general PDEs. In practice, of course, every time you take a new PDE, you have to tune the architecture and the hyperparameters. So it's not so straightforward, but in principle, the method is quite generic. Then we look for the solution among the set of neural networks for a given architecture. So every time I write phi theta, what I had in mind is that you fix an architecture. This architecture depends on a number of parameters, or rather parameters theta. So when I say depends, I mean it involves a number of trainable parameters. So here, theta is not the number of layers or the width. It's really the parameters that we can tune. And the goal is to tune these parameters so as to make these two terms equal to 0 or as close to 0 as possible. All right. So next, we introduce a loss which has some stochastic interpretation. Again, you could write the integral over the domain and the integral over the boundary. So here you would have the integral over the domain of f squared dx, and here you would have the integral on the boundary of g squared dx. So if your boundary is very strange, it might be hard to sample points on this boundary. So here I do as if we could easily sample. If you have a cube or something like this, it's easy. But if you have a boundary with a very weird shape, it's not necessarily easy to sample. But let's assume you can sample uniformly, or maybe you don't want to sample uniformly, but you have some distribution and you sample over the domain. Then you apply SGD as before. So there are many things to be said here. The choice of distribution. Sorry, there is a comment D is equal to 3. Yes, D can be equal to 3, for example. The choice of the distribution. So here I pick uniform for simplicity, but you could pick a non-uniform distribution, and this will influence your training and also the generalization error. So if you don't sample points uniformly over the domain, it means you are going to train more in some region than in some other region. Maybe because this region is more important, maybe because in this region the solution is harder to learn. There could be various reasons to do that. And this is most likely problem dependent. Boundary conditions. So as I said, you need to balance the importance. So here I'm not putting any constant, but in principle, you want to add a constant here, which is going to weight the importance of the boundary condition. And I can show that later. Sometimes if we put a very strong constraint to satisfy perfectly the boundary condition, which looks like a good idea, sometimes it actually hurts the training of the rest. So it's not so easy to find the right balance between the residual inside the domain and the residual on the boundary. And I think that's one of the difficulties with this method. Higher order derivatives. So if you want to compute derivatives of order 2, then it means that you have this d2 of phi theta with respect to x. Okay, and on top of that, during the gradient descent, you are going to compute the gradient with respect to theta. So it means already a third order derivative. And if x is in dimension 100, this is going to be very costly. And theta is in dimension 10,000 or 100,000, because you have 100,000 parameters. It's going to be costly, even though in principle, TensorFlow can do it for you. But still computationally it's going to be expensive. So there are some approximations you can do. For instance, for second order derivatives, Linus Piliopoulos in their paper, they have some ways to approximate the second order derivative by using only first order derivative, or maybe even just the function itself. So you can try to reduce the complexity in this way. Choice of architecture. This is also very important. In fact, in low dimension, at least based on my experiments, feed-forward fully connected networks seem to work pretty well. When I say low dimension, I mean maybe 2, 3, 4, 5 or of this order. But when you go in higher dimension, they are pretty hard to train. In principle, you have universal approximation result, but in practice, you may need very, very wide networks or very, very deep, and it may take a very long time to train. It seems that there are some other architectures that are more efficient for this method. More efficient meaning they are easier to train, for example. So the architecture proposed by Sirignano and Spiliopoulos is reminiscent of LSTMs, long short-term memory networks, which is a popular class of neural networks. But it's not immediately clear why LSTMs, which are, for example, used in NLP, so natural language processing, when you want to process a sentence or when you want to process a time series, these architectures make sense. But when you are trying to solve the PDE, we don't solve it forward in time or backward in time, right? We solve points in time and space. If I go back here, my comment about the fact that x could be replaced by t and x has a consequence, which is that here, when you sample x, it means that you are sampling a point in time and space in the domain. So you really have your grid. Let's do it in dimension 1. You have x, you have t, and you sample points a little bit everywhere, and you try to see if the residual is 0. And if it's not 0, you adjust the parameters of the neural network. Okay, so here there is no propagation of information, let's say forward in time or backward in time, right? And this would be true as well when we look at the PDE system for mini-free games. We are not going at all to try to do this forward-backward structure. Although we may want to solve each PDE iteratively, but for the Kolmogorov-Fokker-Planck, we don't use a forward propagation. I mean, in the sense in time. Okay, so there are some specific architectures that could be helpful. And I think here, if you are interested, there are certainly many things to understand about why such and such architectures are better for such and such problems. One comment is that, that we can make is that you see here, we really need the first order, second order derivatives because they appear in your PDE. So when we were looking at stochastic control problem, for example, in the direct approach, we were taking j of alpha, we were replacing it by j of phi theta, and this was basically j of theta, just a function of theta. So, or the loss, if you want, function of theta. So fine, in both cases, we get a loss, which is a function of theta. It's written as an expectation of some samples, but you see that in the direct approach, we only needed phi theta. We never needed the derivative with respect to x. But here we need the derivatives, and we need the derivatives to be accurate, right? Because if they are not accurate, the PD residual will be pretty bad. Think again about the example I gave. Imagine the true solution looks like this. The true phi solution looks like this. And I approximate it using a neural network which does this, for example. And you see that, okay, in terms of soup norm, I would be very close to phi. But if I check the PD residual, it's probably going to be very bad, or the ODE residual, if you want. Here it's one-dimensional. ODE residual, very bad, very, very large. Why? Because the gradient is completely wrong, right? So solving ODEs or PDEs using this DGM approach is in some sense more difficult because you need the derivatives to be more or less correct on top of the function itself. Whereas when you are trying to minimize J theta, you need to find the correct phi theta, but if the derivative is not correct, maybe it's not such a big deal. It's a big deal for the analysis, you need some regularity, but numerically, maybe it's not a big problem. The points are uniformly, yes, the points are uniformly picked, at least in what I'm presenting here, but in practice, you can pick, for example, a Gaussian distribution, or you can pick a distribution which gives more points in some region when you know that the region is more important than another one. So sampling is indeed a very good question to have in mind. The expectation in the loss is calculated with a Monte Carlo method. Yes, so it's calculated with a Monte Carlo method. And in fact, we don't try, so when we run stochastic gradient descent, we don't try to estimate the expectation perfectly. What we do is we pick a few samples, we evaluate the loss, we compute the gradient, and we do that many times. And we are hoping that in the long run, because at each iteration we pick a few points, we are hoping that in the long run, we are really minimizing the true expectation, but without ever trying to estimate this expectation. So that's the idea behind stochastic gradient descent or batch stochastic gradient descent, mini batch. At each iteration, you pick a few points. Can you reduce PD order by variational formulation? Maybe, I'm not sure what you have in mind, but it's true that if the PD has a variational formulation, meaning that you can interpret it as a solution, so you interpret the PD as the optimality condition for some variational problems, and maybe you can try to solve this variational problem directly instead of solving the PDEs. Yeah, it can be a good idea indeed. But for example, if we think about the mean-field game PDE system, it does not always have a variational formulation. Mean-field control, yes, but mean-field game, in general, it results from a fixed point, and it's not clear that there is a variational formulation. I discussed variational approach for some class of mean-field games, but for general mean-field games, we don't always have a variational formulation. Okay, thanks a lot, everyone, for your questions. So how can we, so maybe just a few words about the architecture. So here I put the architecture as introduced by Sirignano and Spiliopoulos, and you see it's a bit involved. It's not just a pure feed-forward fully connected networks. In particular, you start with S1, and in order to compute SL plus 1, so L is for the layer, in order to compute SL plus 1, you have a few operations to do, right? So actually, one layer, if you want, is composed of sub layers or sub steps. Okay, you can see that here there is this operation which is basically intuitively it's what we call a gate. So it's something that manages the flow of information in the network, and you see that. For example, S1 is going to be plugged here when you are defining S2. So this means that potentially, imagine that H is equal to 0, then this term disappears, and Z is equal to 1, then SL plus 1 would be exactly equal to SL. So you allow the neural network to keep some memory from the previous layer. Right? Here we are not talking about iteration, it's really about how the information flows between the layers. And what this operation here allows is to keep information from the previous layer and maybe information that is not modified at all, right? So you can keep some information from the very first layer up to the almost the output layer of the neural network. And this you cannot do in a feed-forward network, because you do some operations and you keep transforming in this way. Or at least it's not so straightforward. What you see in a standard feed-forward fully connected network is more something like this here with the activation function, right? So here you recognize W times S, which is the previous layer, plus B, so the bias, and some activation function. But in this architecture, there is much more to that. Okay, so what about the mean-field game PDE system? So here I rewrite the system on the time interval 0t and the torus. Remember the definition of the Hamiltonian. The first equation here is the backward one. Second equation is the forward one. Before solving this system, I will start with the ergodic version. So actually, I think in the third lecture, probably Francois had a question about the ergodic system. So I said that if you have a solution for the ergodic problem, you can use that as an initialization for the time-dependent problem. And vice versa, if you have a solution to the time-dependent problem, you take the solution around the middle of the time horizon, and very often it's a good guess for the ergodic solution. In fact, there are some existing papers. I'm thinking in particular about the paper of Kakache et al., where they have a numerical method for ergodic mean-field games. So there are some methods, and there are some cases where you can solve the ergodic version. And here what I'm going to present is a deep learning method for the ergodic system. And I'm going to show some numerical examples. So the goal being to solve it in high dimension, which would not be accessible using, for example, finite differences, because making a grid of points in dimension 20 with 100 points, it would mean, so maybe I can stress that. Imagine you want to use the finite difference scheme with maybe 100 points. 100 is not a lot, actually. Maybe you want 1,000, but let's imagine you want 100 points in each of the, I don't know, 20 dimensions, for example. Then how many points do you need? Well, you need 100 to the power 20, right? Which is pretty big. So if you try to put that in your computer, I don't think your computer can handle this, right? Or okay, you can take even higher dimension, take dimension 30 or 100, then you get 100 to the power 100. Okay, it's a lot of points. Even if it's feasible in terms of memory, in terms of computation, it's going to be very slow. But anyway, 100 to the power 100 is not realistic. So here's the goal, is to use neural networks. So we are going to parameterize the functions. So U and M are going to be parameterized using two set of parameters. The ergodic constant lambda also needs to be parameterized, but this is just one real number. And you see that the idea will be to take the number of parameters smaller than 100 to the power 100. Otherwise, we have the same complexity as if we were making a grid. So the idea is to take a relatively small number of parameters. And why could this work? Well, you can imagine that maybe if the solution is quite smooth, actually you don't need so many parameters to describe it. But it's just that you don't know the shape in advance, right? So you need some flexibility. You need some architecture which is flexible enough to fit the shape of the function with assumed parameters as possible. And this could work even in high dimension, because your function is some kind of surface in a very high dimension. But if the surface is pretty smooth, you don't need to know the value at every point one by one somehow. You just need a small number of parameters to describe it. Think about a linear function in dimension 100. you just need a few parameters, right? So of course, if the function is linear and you know the parameters, you know that it's linear in advance and you know the parameters, just look for a linear function. But if the function is approximately linear, then, well, then what do? You need some class of parameterized functions that will be able to learn the shape somehow by minimizing the residual here. Okay, so yes, and there are analogous PDE systems for the MFC problem. So I'm not writing it here. You can check the references, or you can check the references I will give for the plots later on. So here is an example inspired by a paper by Almula, Ferreira, and Gomez, which is on the torus for the ergodic Miffy game, and they have an explicit solution. So I mentioned that when you're looking for explicit solutions, linear quadratic is a good maybe playground. But if you are on the torus, then linear quadratic does not really work. If you take linear quadratic on a torus, you need the whole space to have the explicit solution. But this example here has, so why do you need the whole space? In particular, the control is a linear function. A linear function is not really periodic, right? Except if it is constant. So if you, by definition, the solution must be periodic. So linear quadratic does not work. But here for this one, so if you choose the running cost in this way, so alpha square is a cost for moving. ln here is the cost of crowd aversion, which is local because it depends only on m at x. And then f tilde is a kind of spatial preferences, function encoding spatial preferences, which here is given as a sum of trigonometric functions. Trigonometric functions are periodic, so that's nice. And it turns out that in this case, you can do the computation. The solution to the PDE system is given by u is equal to the sum of sinus, and m is equal to basically a Gibbs measure, so exponential 2 to the u divided by what you need to have the normalization. So here there is one thing that I didn't spend much time on, but you see there is a normalization constant here for m and for u, because, for example, u is involved only through its derivatives. So if you don't put any normalization, then if you find one solution, you'll find infinitely many because you can shift by a constant and it's still a solution to the PDE system, right? So that's why we need some normalization condition in order to have uniqueness of the solution. Otherwise, you have non-uniqueness, and the neural network might, so if you have non-uniqueness, then we don't really know what we are computing, and the neural network might be just oscillating between different solutions. All right, so in this case, here is the result of a numerical experiment in dimension 10, and we have the explicit solution, so we can compute not just the residual of the PD, but really the L2 error on U and on M, or mu here. So mu is equal to M between the solution computed by the neural networks and the true solution given by the explicit formula. And we see that here's the loss. Okay, it's not extremely small, it's 10 to the minus 2, and I'm sure you can make it smaller by playing with the hyperparameters, but at least it seems that it is, I mean, it's not, it seems, it's, okay, it seems that it is converging, because convergence would be the asymptotic property where it really goes to 0. So here it will not go to 0 because you have some kind of incompressible error due to the architecture and other accumulation, other numerical errors. But the error is very small. So again, this is not just your loss function, this is the L2 error. And so it means that you are at distance 10 to the minus 2 to the true solution. Okay, and the true solution is not, I mean, it's not, okay, you could say that linear is kind of simple because it's really very flat, but this one is a combination of signs, so it's not so trivial to learn at precision 10 to the minus 2 in dimension 10. Another example, this time without explicit solution. So this one is inspired by sorry, maybe there is a question or a comment. Yes, so there is a question. Can we use L1 to measure the error? Yes, I think we can use L1 to measure the error, definitely. But anyway, the error here is something that I measure a posteriori. It is not related to the algorithm, right? The algorithm, okay, those are two questions. Here, the error I'm talking about is really the error between the U learned by the algorithm and the true U using the explicit solution. So this one is a measure that I do, but it's not used for the training, right? It's more a measure of success of the method. In the training, here I really use this DGM loss that was written here, except it's for the 2PD system. So as a 2PDs, so you combine everything as well as the normalization conditions. And here we could say, well, can we use L1? I think you can, but the drawback of the drawback of L1 is that it's less smooth, right? So I think it would be less smooth. So probably square is a better idea. But in practice, sometimes I've seen L1 work as well. So I don't have a really, strict answer here. Okay, thank you. So again, this is just for the measure of success if we know the solution. Now, what if we don't know the solution? So here is an example. It's pretty similar, except that you see here, instead of having a log, you have just mx squared. And then you have a sum of sine and cosine, which are trigonometric functions. So in particular, they are periodic. And here is a result in dimension 30. And this is really for the residuals, right? What I'm not showing, but what should be here as well, is the normalization. So you also have two error terms for the normalization, and also for the periodicity. So to ensure the boundary condition, sometimes you use an extra penalty term, for example, for periodicity. Sometimes you can ensure it by construction also. So it's possible to design neural networks that are periodic by construction. In this case, you don't need to add any extra penalty in your loss function. But if you have, and it's also possible sometimes for Dirichlet, Neumann boundary conditions, you can impose them by construction of the neural network using some specific architecture. But in general, you can do that by penalization. But of course, the price to pay is that you have to put this penalty in your cost and you have to choose the coefficient of the penalty. Okay, and you can go even in higher dimensions. So here you see, for example, the behavior of the residual for the AJB. So it's always going down, but sometimes slowly, sometimes quickly. Notice that this is a log scale on the right. So in some sense, if it's going fast in the low regime, it's actually very small changes, but it's hard to go to the solution when you are in a very slow level of the error or of the residual. And you see that here, for example, the loss for the KFP is almost increasing, right? So you could say, well, then this is going wrong, but we can see this behavior very often when you use this method for the PDE system, because it's a system. So actually, you try to minimize the total residual, but maybe when U is changing, it is kind of bad for M. So M had found a good approximate solution, but then U is changing. So then the residual for M is increasing, right? So they are really related to each other, and you cannot minimize, you cannot solve the whole system without paying this price of tuning both of them. Any estimation of time of computation? It's a good question, thanks. I don't remember for this experiment. But I would say probably a couple of hours, something like, it's of this order, couple of hours, maybe less than that if you use GPUs and you optimize the code. Yes, something like that. So it's not days of computations and not just a few minutes. I haven't tried very hard to optimize the codes, to be honest. So, and the techniques keeps improving. So maybe Probably now we can do even better than what we could do a few years ago when I started. When I started, I didn't know anything about neural networks or TensorFlow, so I learned along the way, and along the way, TensorFlow and other libraries have developed a lot, as well as computational power. So yes, I think now it's possible to solve in very high dimension in a very efficient way. And in their paper, Selignano and Spiliopoulos, I think they go up to dimension 100. I've seen some papers going up to dimension 1000. So it's really possible to go very, very high dimensional, but probably not for any PDE. Okay, in general, there is some hidden structure. I mean, there is some structure. The solution has some structure. And for example, if the solution is constant, then learning a constant in dimension 1000 is maybe not so hard, right? So usually it's not a constant, but my point is, if the function is very smooth and etc., and if you have some specific structure, it's not that hard to imagine we can learn it even in high dimension, but still it's not trivial, right? You cannot make a grid. So neural networks are really helpful to approximate and to learn these solutions in high dimension, right? Maybe the solution in the end is not so complicated, but how do you approximate it? How do you learn it? Well, it seems that neural networks are helpful in that case. Okay, by the way, about computational time, just to have an order of magnitude, in the past few years, there are many breakthrough papers. I'm going to cite some of them later, particularly using reinforcement learning. Some of them, they take months of training, right? So you train on hundreds of GPUs for several months. So here we are very far from this order of magnitude. Okay, the last example that I want to give, crowd trading. So maybe I will go a little bit quickly. This is another example, but different from the ones I've presented before, where you have some price impact. So you see this term here that I mentioned earlier, the average action impacts the stock, and then it is going to impact your portfolio. So, oh no, actually we still have 45 minutes. All right, so, well, anyway, I'm not going to spend too much time on this. Sorry, actually the code is for the ergodic PDE system. So I'm going to show the code for this case, but let me illustrate this price impact crowd trading model. So at the beginning, it's a model in dimension 3 because you have S, Q, and X. Okay, there is one extra question. So here I didn't use any, so the question is about parallel computing. I didn't use any parallel computing and sophisticated software. It was implemented in plain TensorFlow with GPUs, but not a lot of GPUs, maybe just a few GPUs, and then it runs in a few hours. But indeed, if you use some really optimized softwares, I mean, some really sophisticated softwares, maybe you can get it running much faster. Okay, so in this model, I was saying it's three-dimensional, S, Q, and X. But in fact, okay, so it's really three-dimensional, but in fact, what Cartea and Jai Mungal proposed is to guess the form of the solution and to guess it right. And the form of the solution they propose is the following one. So X plus Q, S, U, TQ. And it turns out that if you make this guess with U, so here the key point is that U is a function of T and Q only, right? So it's a function of a one-dimensional input besides time. This U solves an AJB equation, which is one-dimensional. Okay, so Q is just a real number. And so you are back to a one-dimensional PDE. And even more than that, in fact, this PDE is quadratic. And so we are back to a situation where we can apply this LQ approach. I mean, the approach we used in the LQ setting, and we can find really the solution. Oh, sorry, in this one, yes, in this one, it is linear quadratic. I didn't write the solution here, but it is linear quadratic, and you can really have a solution up to solving an ODE system. Then you go back to your price impact model and you say, well, I need new bar, which is the average action. So the optimal control for one player will be given by the derivative of the value function. I integrate with respect to M. And so I get this term for new bar, which is going to impact the price, right? And new bar appears here in your AJB equation. So, okay, this will be for the AJB equation. And for the KFP equation, here you have this, this expression where you recognize the optimal control here. Okay, so you can check all these computations, and the bottom line is you end up with a forward-backward PDE system. So now it's not ergodic anymore. It's really between time zero and time capital T. You have a terminal cost, and the terminal cost, by the way, I could have mentioned that. What is the interpretation of the terminal cost? What is the interpretation of the terminal cost? Well, you get oh, sorry, actually you want to maximize. So this is a terminal payoff. So you want to maximize the product of your inventory and the price of the stock. This is more or less cash if you want, but you want to minimize your position. So you want to have a small inventory close to zero. So you want to basically liquidate, almost liquidate when you are close to the time horizon. But of course, all these terms as well with the running costs are balanced. And so maybe you don't liquidate perfectly your portfolio at terminal time. Again, this is a toy model, so I'm not saying this is exactly what traders do in practice, but it's just to capture some features of crowd trading. So you end up with this PDE system. It turns out that it has an analytical solution up to solving ODEs. And what is the main difficulty compared with what I've presented before? So first of all, there is time. So it's not the ergodic system. And there is a non-local term here. I need to compute this new bar in order to plug it here, right? So it's not a local dependence on the distribution, meaning that if I have a neural network for U, let's say U theta 1, if I have a neural network for M, well, here I'm going to need to compute the partial derivative of U with respect to Q, and then I'm going to integrate these two in the space, in space. Q is the space variable, right? So I'm going to fix time and integrate in Q. So one way to do that is to use Monte Carlo samples. So in other words, here you have Q, you have time, and for one given time, you need to sample various Qs randomly in order to estimate this quantity. I mean, when I say you need, I mean it's one way to do it, but maybe you can find other ways. For example, you can estimate this new bar along the way and try to learn it, and that's maybe more efficient. So in fact, this problem was solved in this paper of Al-Aradi et al. And they have some way of parameterizing the neural network in a smart way. And here the results I'm going to show have been somehow simulated directly with the basic architecture and without this trick. And we see that so on the left, this is a neural network for M. I mean, this is the output of the neural network for M as a function of T and X. So X is actually Q. And the neural network takes the two inputs and give an output. And this is the shape of the output. So you see that people start, I don't remember. So on the right, we see a little bit better. On the right, it's a view from above. So people start with a position roughly equal to 4 in their inventory, and they end up with a position close to 1, more or less. And furthermore, there is a concentration of mass because at the beginning, the population is quite spread out, and then it concentrates towards 1. And the dashed line in red that you can see maybe here is the mean computed using the linear quadratic ODE system, right? So I mentioned that using the LQ ODE system, you get the behavior of the mean, maybe not the behavior of the whole population, except if it is Gaussian. but at least you can plot the mean, and you can see if the mean follows the means that you get numerically with a neural network. You can also look at the control. The control, we know that it should be linear because LQ structure. And furthermore, we can solve the ODE, and we can see that the control is learned pretty accurately. So in fact, we don't learn the control. What we learn is U. So we learn the control, we learn the value function U, and then you compute the partial derivative with respect to Q. You divide by 2 kappa, and this gives you your candidate for the control as a function of T and Q, right? So you can recover the control from the PDE, from the solution to the PDE system. Okay, let me illustrate. So I think that's all I wanted to say. Yes, I have a few more general comments about this DGM method. So yes, introduced by, before I show the code, so introduced by Sylvianos Piliopoulos. In fact, they have some results of convergence, 2 types of results, more precisely. One is by density. You know that there will be a neural network approximating the solution to your DGM, I mean, to the PDE, right? And there will be a sequence of neural networks that minimize the loss, provided you take big enough neural networks, right? If you want to have asymptotic convergence. Conversely, and maybe more interestingly, you can show that if a neural network, or actually any function, approximately solves the PDE, then it is an approximation of the solution, right? So this is more like some kind of stability or some kind of result that says that if you approximately solve the PDE, then you are close to the true solution. But this has nothing to do with neural networks, in fact. But this says that if you see that the loss is small, then it means that probably your neural network is close to the true solution. Because in the end, the PDE is just a way to describe a function, right? So what you really want is to be close to this function. It's not to, so, I mean, I think you don't care so much about the PDE. What you care is about learning the solution, right? So this result tells you if the residual is small, so if the loss is small, then you are approximately equal to the solution. Similar analysis for mean-field games. I think this is for finite state mean-field games. I think that it remains to be done for continuous space mean-field games. But obtaining rates of convergence is difficult. I think these analyses are mostly asymptotic in general. So saying you take big enough neural networks, then it converges. But how many neurons do I need? This is a difficult question. The full generalization error, including the optimization and estimation errors, is a challenging question. And last comment, you can apply this DGM to other settings. So, for example, in this paper, Amal worked on the mean-field optimal transport problem using this DGM approach. And the idea is that instead of having a terminal cost, you have a terminal density, but you can impose it. I mean, you can impose a penalty, which will drive the solution towards this correct terminal condition, and also the finite state master equation, as I will discuss next. All right, so let me show briefly this code here. Okay, one thing I wanted to show actually before that on the previous one, I will reconnect. So one thing I wanted to show, so I did this very bad change, which was to put a sigmoid activation function. So let me remove that, and let me show you what it gives when you remove this sigmoid activation function. So now it should work very well after. So this is initialization. Now you see it starts learning, and it's almost like a movie. I think after maybe 1000 iterations. So here you can already see now it is taking the correct shape and changing iteration by iteration. Okay, and after 1500, 600 iterations, it's already pretty good. So let me stop it here, and let me do what I said earlier, which is to put a large coefficient in front of the boundary condition in the loss, right? So here, let me put maybe 100. Maybe it's even too much. Let's see. I put 100, which means I give a weight 100 to satisfying the boundary condition and the weight 1 to satisfying the ODE inside. So you see what happens is immediately, indeed, it satisfies the boundary condition and it's really stuck there, right? So the neural network does not want to move from this point because it would pay a very high cost in terms of loss. So it sticks to this, but the consequence is that it does not really manage to optimize the rest, right? So now you see we are already at like 3,000 iterations. Okay, I put a stopping criterion at 3,000 iterations. Now it is learning a little bit, but you see it is much slower than in the previous case. So one may think that imposing the boundary condition in a very kind of strict way would help the neural network, because that's the intuition from finite differences. For example, you start from time 0 and then you propagate information forward in time. But actually, apparently, the neural network doesn't really work in that way, right? It doesn't really learn in that way. So if you impose strictly, if you really want the neural network to match the initial condition, fine, it is going to do that. But then for the rest, it's going to struggle, right? And that's probably because the landscape, if we could visualize the landscape of the loss, it might be, for example, very steep, and then the neural network is kind of stuck in a bad local minimum, and it takes a long time. So this is even more true when we discuss PDEs, actually. And in this DGM method for the PDE system, you have two PDEs, so you need to balance their importance. You have two normalization conditions or initial and terminal condition, and you also have to balance their importance, right? And you see in the previous example, if you put a weight which is too large, maybe you are going to wait a very long time. In principle, it should still work, but you may have to wait thousands or tens of thousands of iterations until the neural network finds a way towards a better minimizer, right? And you may see some plateau for a very long time. Okay, so I don't have a good answer about how to balance these terms. I'm just saying it's important to keep this in mind. So for this notebook, again, I appreciate the help of Yuchen, who helped me to formalize this notebook and put some comments. And here you can find the model that is described. So it is the model for which we have an explicit solution. So you see here, P is equal to U, actually. So P is the sum of sign, and nu is equal to mu in the slide, or m in the slides. It is this Gibbs measure, right? So P is the value function. Nu is a distribution. Sorry for the difference between notations. And lambda is the ergodic constant. So really the structure is quite similar to what we had for the ODE. So in fact, we have here one part, but it's more involved because it's for a mean-field game. So here the code is split into several parts. One part is for the model, so the Hamiltonian and the drift in the Fokker-Planck. So you can change these terms depending on your model. And then there is this DGM solver, which is basically creating three neural networks, P, nu, and lambda, but lambda is a neural network with just one parameter and no input. In fact, there is just one parameter. It's a constant, but here we call it a neural network. And P and nu are neural networks which take as input the state variable. There is no time because this is for the ergodic problem, right? Then we sample. So here, what we do is we sample between xmin and xmax uniformly. So xmin is 0, xmax is 1, because we are on the unit torus. And this is for a one-dimensional example. Okay, so exercise, generalize it to other dimensions, and it works in higher dimension. I showed you some results, so you can really extend it in higher dimension. This is to compute the derivatives. So here you see we need a double gradient because we need the Laplacian, right? In this ergodic system, there is a Laplacian, so we need a second order derivative. And here it's computed really naively, in the sense we really use automatic differentiation in TensorFlow to compute the first order derivative and the second order derivative. Here they are one-dimensional, so it's not really costly. if you are in dimension 100, using second order automatic differentiation would be quite costly. And in particular, you don't need the full Hessian matrix, you need only the diagonal, etc., etc. So there are many things to improve to make it work in higher dimension, but here it's going to work in dimension 1. Loss function, so KFP residual. So here, this is really the implementation of the KFP residual, AJB residual, same thing. So you see the ergodic constant, etc. And then the boundary conditions. So here we sample, well, actually, we don't need to sample because here it's in dimension 1. So you just have the point 0 and the point 1, right? But if you are in a hypercube in very high dimension, you are not going to take all the possible points. So you sample points on the boundary. You compute P, you compute nu, and then you want P at 0 to be equal to P at 1, because this is the periodic boundary condition. And last, you have the normalization. So you want the integral of P to be 0, and you want the integral of nu to be 0. So the integral here is computed using the mean based on Monte Carlo samples, right? Estimated by Monte Carlo samples. At the end, the loss is a combination of all these terms. So you see loss value here, we keep adding quantities plus equal here in the loss value. And the final loss is composed of many terms. And here you have some coefficients to weight the importance of the periodic boundary condition, the normalization, and that's it. And the first one has a coefficient of just 1, but you could also add extra coefficients here. And really, these coefficients are really important. Like if you put too large or too small values, it may slow down a lot the training. One-step gradient, this is to train P, U, and lambda, and then training is just a loop over the gradient. There is one question, does the geometry of the domain influence the result? So yes, in the sense that the geometry of the domain changes the solution, the true solution, right? If you are on a periodic domain, if it's a cube or if it's something else, so the solution is going to change. And it also influences the learning, I think, and the way you implement the algorithm, because you need to sample points on the boundary, and this might be complicated if the boundary is not flat, for example. Okay, and here we use a simple feed-forward fully connected network, 3 layers, 3 hidden layers with 100 neurons each, but you can play with that. And this is not the complicated architecture proposed in the DGM paper, right? In small dimensions, this architecture goes well, as we are going to see. In higher dimension, I think feed-forward fully connected tends to be hard to train. It has trouble finding the solution, as far as I can tell, based on some experiments. Okay, and here I'm not going to run it, although it's not very long, actually. Even though the number of iterations seem large, but it runs in just a few minutes. So number of parameters is pretty large, so it's clearly over-parameterized. I mean, yeah, it is. There is a large number of parameters. I cannot say it's over-parameterized because we are trying to approximate sine and cosine using a combination of linear and sigmoid function. So you would need infinitely parameters to be infinitely precise, infinitely many parameters to be infinitely precise. So it's not over-parameterized, but there is a large number of parameters. And you see the loss, sorry, let me go back again. The loss starts at a pretty high value, 388, and then it decreases until 10 to the minus 3. So if you look at the plot, this is, sorry, so this is for which one? This is the total training loss somehow, and you see it does have some plateau for a few thousand iterations, and then it finds a way to a relatively small loss. If you look at the loss just for AJB, it looks like this, and you see sometimes it goes down and then goes up. So this is not very intuitive. It does not, well, sometimes it happens, but here it happens even in standard deep learning, but here it happens even more because you have interactions between the AJB and the KFP. So sometimes the AJB has learned what it believes to be a good solution for the current M, but then M changes, and so AJB loss increases, and then AJB has to, the solution to the U has to change again, right? So there is really some non-linear, some non-monotone, let's say, evolution for the KFP as well here. It's even more non-monotone, right? Okay, boundary conditions, etc. Let me just show you the solution. So for this one, we know the exact solution. It is the dashed line. So we barely see it because it overlaps with the last iterate, which is very precise. You see at iteration 0, it's not good. Iteration 1, it gets better. Iteration 2, it gets better. So you see just a few iterations, but still the green line is not very close to the solution. And then after thousands of iterations, it gets really close. And same thing for the distribution here. You see at the beginning, it's kind of constant, but oscillating between different values. And then at the end, it really catches the shape and manages to learn that. So what I was saying earlier is while U is not good, so if U is not correct, M cannot be correct, right? Because M is trying to solve the KFP or the Poisson equation associated to this U. So if U is not correct, M cannot be correct, and vice versa, right? So the two neural networks are really depending on each other. So another question, what about the sigmoid activation function in the case of high dimensional? Yeah, so in high dimensions, there is a curse of dimensionality. So, okay, in high dimension, the bottom line is you need typically deeper networks, and for deep networks, the choice of activation function is more has more influence. In particular, for deep networks, you may easily have vanishing gradients, exploding gradients. So I think this depends on really the experience. Maybe tanh hyperbolic tangent can be better than sigmoid, and there are some arguments for that. But yes, then I think I recommend just trying different activation functions and seeing what works best. But it's a good thing to have in mind, maybe. Okay, so I will come back to this just a bit later. Maybe I can mention this right now. This interaction between U and M. Actually, you have two neural networks interacting. In some cases, you have a variational interpretation for the PDE system. And so this led us with Singo and Haoyang Cao to study the connection between Minfield game PDE system with neural networks and GANs, generative adversarial networks, because here you have two neural networks kind of competing or helping each other. And one of them is a distribution, right? M is a distribution. So this seems very connected to generative adversarial networks. So maybe I give the reference a bit later in the slides in case you are interested. Okay, let me go back to the slide. So that's about it for the codes for this morning. There will be more this afternoon, but for this morning, that's it. And we still have some time. So let me discuss the master equation. So the idea, as I mentioned in the first lecture, actually, is that U is a function of T and X, okay, because M is a deterministic function of time, and it depends implicitly on M0, right? So if you give me M0, if you give me time, and if you tell me which control you are using, then I can compute M at time T for this M0 and for this alpha, right? By solving the Fokker-Planck equation. But maybe in some cases, I would like to have an explicit dependence of U on the distribution. And in that case, so here I use a notation mu instead of M, sorry. So let me write mu and mu to be consistent with this. And sometimes you would have an explicit dependence. So this is done through the so-called decoupling field or the solution to the master equation. Because it turns out that this U defined in this way satisfies a PDE, but it's a PDE on the Wasserstein space of probability measures. So it's quite complicated. I presented it in the first lecture. Here, I'm not going to rewrite it in the continuous space case. I'm going to write it in the discrete space case. So motivations, convergence of n-player games, There are also some papers on large deviation principles by François Danlaker and Kavita Ramanan, and then some follow-up papers. It's interesting when mu zero is not known or when you have common noise. So in particular, for me, is a practical motivation, let's say from the point of view of numerical method. Why would we want to compute this abstract object, which is a function of a measure, right? Well, I think the practical motivation is if we compute it, then we will have similarly a control, which will be a function of t, x, and mu t, meaning that as a representative agent, I know how to react to any time, any position, and also any mean field distribution, right? Which is not the case when I consider just Markovian controls functions of t and x, my own state. So if there is common noise affecting the distribution, I cannot predict the evolution perfectly. Or if I don't know the initial distribution, then I cannot solve the mean field game in the way I presented so far, at least. Right? So these are situations where you might be interested in solving really the master equation. So how can we compute mu? I'm going to start with the case of finite state. So when it's finite state, the mu is an element of the simplex. So this is also what I denoted before P of x. When x is finite, is a set of histograms. There is an evolution from mu given by a transition matrix. So here's notation is a bit different. I think in the first slide, what I was writing was something like pt times mu t. But if you transpose everything, you get this q. Okay, if you use row vectors instead of column vectors for mu. Okay, and what is the master PDE for you in this case? Well, it takes the following form: terminal condition, and then a backward equation, so minus the partial derivative in time. You see the Hamiltonian, and then there is a term which involves the transition or the average transition, so I'm not defining everything here, and in particular, this partial derivative with respect to the measure. But because we are on a finite state space, the measure is a histogram, it's a vector in dimension number of states, and so the partial derivative of mu is just a classical partial derivative, right? So partial, so u here, you can view it as u of t, x, and then mu1 until mu d if you have d equal to the cardinality of x. Okay, so mu is a vector, and then I can take the partial derivative with respect to mu I, for example. So here, nothing complicated for the representation of the distribution and for the partial derivative. Everything is classical, so it's a classical PDE. But if D is large, meaning if the state space has many states, then it will be a PDE in high dimension. So this is a motivation to use the DGM method. And I'm not going to write the laws, but it's exactly, we mimic what we did in the previous case for this PDE. Here, I revisit the example of the cybersecurity model that I mentioned at some point. So this is a model in which you have 4 possible states. You can be infected and defended, infected and undefended, and same thing for susceptible of infection. So here we are talking, they are talking about computers being infected by a virus. And then your control is the rate, is that you want to become protected or you want to become unprotected. And this happens at some rate. It does not happen instantaneously. The model is in continuous time, but we don't have singular controls. You just control the rate at which you are going to jump to the other state. So this is one example, which is similar to the SIR model I discussed in the first lecture. It's continuous time, finite state, right? The mean field interactions are through the probabilities to be infected. So a bit similar to the SIR model. The transition from susceptible to infected happens more quickly if there are many infected computers than if there are no infected computer. This is the mean field interaction aspect. And last, the running cost is a combination of a cost to defend yourself, to pay. You have to pay maybe some software to protect you from viruses, or and rather a cost for being infected. So if you get infected, then you pay a cost because you have to fix this problem. Okay, so for this problem, we can apply this. We can write fully the master equation, and we can solve it using DGM, which is the PDE residual plus the terminal condition. How do we check if it is correct, right? So this is not very high dimensional. For solving a PDE in dimension 4 could be difficult, but here actually it's more a system of 4 ODEs in some sense. So yeah, you can view it as a system, so you can reduce the dimensionality, but still, if you view it as a PDE in dimension 4, it's complicated to solve. So DGM can be interesting, and it would be even more interesting for higher dimensional problems. But how do you check if the solution is correct? So what you can do is this U theta is going to be the result of DGM. Okay, so we are going to use DGM, we get this neural network. The neural network, we can evaluate it at any input, right? So any t, x, and mu. I can plug whatever I want and evaluate it because there is no discretization. Okay, so the mu I'm going to plug is the mu coming from the true solution somehow. So what I do is I fix M0, solve. So when you do that, you have an MFG with a solution mu that depends on M0 and U that depends on M0. And this solves an ODE system, actually, because it's a finite state continuous time MFG. So if you give me M0 and I know the terminal condition, I can solve the forward-backward system, no problem. Okay, I get a flow of distributions, so mu M0t, and this one I can feed it in U. So U, T, X, mu, starting from M0, like this. And in principle, this should be equal to U for the same M0 at time T and position X, because that's how we define the master field actually. So I can compare the solution along one flow for one mean field game with one initial distribution. Okay, so if I fix the initial distribution, there is no problem. But again, the interest of computing, the main point of computing this object is you can evaluate it at any mu. In particular, if you don't know M0 in advance, it's fine. You pre-compute U theta, and when the game starts, you look at M0 and you start plugging your M in U, and you find the value and the associated control. So if you do that, actually, you can check that so you can do that for different M0. For example, M0 0.25 for each state. You solve the forward-backward system, you get this evolution on the left for mu. So you see that here there is one state that is going to dominate. It is a state mu3. If I go back, mu3 corresponds to 0, 1, 2, 3. It corresponds to undefended and susceptible. So this is a situation in which at the end, most people do not need to pay a protection and they are not infected because the virus is more or less disappearing. But not completely. There is still some infected people. Okay, and on the right, this is a value function. So at the end, it is 0 by definition, all right? But before that, it solves the backward equation. So it's an ODE in dimension 4. But I can also evaluate the computed master field. So the U, I evaluate it at M. And if I do that, I see that the U coming from the master equation matches the U coming from the AJB ODE, actually, here. They match very well for each of the 4 states. And you can repeat that for various initial conditions, like concentrated on one of the 4 states, etc. And every time you see that the shape of U changes, the shape of M, but also the shape of U changes. And every time the neural network is well aligned with the solution of the ODE. Here is one more example just to show the result, but I would refer to these lecture notes. Again, this was for the AMS short course that François organized a few years ago. And this is an example for a master equation for a mean-field game with two states where there are multiple solutions. So the master equation has multiple solutions, but there is only one which satisfies an entropy condition. And it turns out that the neural network finds, using this DGM method, just from the directly out of the box, you change the model, you change the definition of the game, and it's going to find the entropic solution. So I haven't investigated further. That seems to be an interesting feature. Maybe there are some cases in which it doesn't find the solution, I'm not sure. But here you see it finds this entropic solution, which is discontinuous. So the entropic solution has an analytical formula. It is discontinuous. And the poor neural network cannot do something discontinuous because the activation functions are C infinity. So it cannot do anything discontinuous, but it is really trying to find something that almost jumps from one point to the other as we increase the number of iterations. Okay, so the analysis of this DGM method for finite state mean-field games, actually, it's a work in progress with Asaf Cohen and Ethan Zell from University of Michigan, but we are tackling several aspects, so you can see the paper soon. And we also tackle one form of the deep backward dynamic programming equation that I'm going to show next. And personally, I'm also interested in applications to macroeconomics. So we have a joint work with Jonathan Payne and Sebastian Merkel, where we apply this method, what I have described, and as well as other methods to macroeconomic models like Ayagari and Kruser-Smith models. So you can check the draft. It's a draft, and so we would be happy to have comments or feedback if you have any. There is one question. The derivative of Carl U with respect to the measure is computed with automatic differentiation. Yes, absolutely. Thank you. It's a good question. So I mentioned that this partial derivative is classical, and it is done using automatic differentiation, at least in this implementation. And here it's first order, so it's okay. You could have second order derivatives, maybe if you have common noise, but here it's first order. Okay, so I already discussed this in the previous lecture, so let me just give a few more details. Now we take a model in continuous space. So there will be a question of how to approximate the distribution, right? If it's finite state, it's okay, but in continuous space, it's more tricky. And if you have common noise, that's another motivation to study the master field, because you cannot predict perfectly the evolution of the distribution. So in that case, you can write the master Bellman equation coming from dynamic programming for this value function that I mentioned several times. So here is the Bellman equation for this mean field control problem, not the game. Okay, so it's really an optimal control problem for the distribution. Below, you can find the definition of F, G, and H. I will skip the details, but you see that, what do you see? There is a time derivative. There is a derivative with respect to mu. If you have common noise, there is a second order derivative. And there is also some mixed derivative here in X and mu. Okay, and the terminal condition. So how can we approximate this V and solve the backward equation? So one way is to approximate mu by an empirical distribution. But even when I say empirical distribution, it's not very satisfactory because I don't know how to put that in a computer, strictly speaking, right? What I can do is I can consider all the inputs, x1 to xn, and I can say, well, I want V to be a symmetric function. And in fact, this is also the intuition behind the Lyon's derivative. So here you can check the book of Carmona and Delarue. I don't remember the page number, I'm sorry, but I think it's in chapter 5 for the volume 1, and it has a lot of information about the Lyon's derivative. In particular, you can justify it by starting from functions with symmetric inputs and passing to the limit, and you get really V as a function of the empirical distribution seen as a measure and not seen as a vector of n inputs. So that's the intuition behind using symmetric neural networks. For example, deep sets, PointNet have been introduced for that. And there is one simple way to get symmetric neural networks, which is by taking the sum. So you take your input of length n, you apply a neural network or some transformation on each of the inputs one by one, and then you sum that. And when you sum, you have a symmetric function. And then you take this sum and plug it into a more complicated network. So you can do this kind of operations to have, in a very somehow simple way, you build in the architecture the symmetry with respect to the inputs. Okay, I will skip the algorithm because it's similar to the deep backward dynamic programming I have described before. I just want to mention so you can see more details in this work, and also the analysis by Maximilien Germain and Louis Enfam and Xavier Varin. Some results about convergence. So I've discussed the deep Galecki method, deep backward dynamic programming method, many open questions for mathematicians. So if you are interested, I think there is a lot of interesting work to do to understand better these methods. There are other papers, in particular a work by Ruth Otto and Osher and collaborators. What I mentioned about MFGs and generative adversarial networks, so this collaboration with Singuo, and then a few surveys in case you are interested, not only for mean field, but also for optimal control, deep learning for optimal control. So I think we are done with the slide deck number 5, and this afternoon we can do slide deck number 6 about reinforcement learning. If you have some questions, I still have time. Thanks a lot for your attention.
Thank you very much, Mathieu, again.
Thank you.
So if there are any questions, please feel free to ask.
Thank you. So there is a question. So according to your experience, which library is more effective, TensorFlow or PyTorch? It's a very good question. Actually, I have more experience with TensorFlow and PyTorch personally, but I heard that PyTorch is very effective, and maybe sometimes it's easier to implement the methods. So yes, sorry, I don't have a good answer. Also, it may be a little bit of personal taste, so I don't know. But I think it's so the examples I give are all in TensorFlow. Because I started with that, so I'm not claiming TensorFlow is better than PyTorch. It's just that I started with that and I wanted to have a uniform style over the different examples. So I provide everything in TensorFlow, but if you make experiments in PyTorch and you notice some improvement, or I would be happy to hear about that. Thank you. So one more question. About mean fielding. So maybe effective for understanding emerging patterns in collective rational behavior, for example, lanes in crowds or flocking, and or yes, fast for yielding and tractable approximate Nash equilibria. Yes. Which of FPSDEs and PDEs would computationally fit? Yes, with each of these two aims. So it's a very broad question. Thank you for asking. Okay, so I think there are advantages and drawbacks on each side. So yes, indeed. So let me just recap the question. From my understanding, at least, is the motivation from meaningful games is to basically have approximations of n-player games, right? So the point is maybe not just to solve a meaningful game accurately, but to know which solution is going to give us something good when we plug it in the n-player game, right? So for this, I don't know which one is going to be best. One comment maybe we can make is that for FBSDEs, we are really studying the solution along the path of controlled diffusion. So in some sense, maybe we are doing less effort to try to learn the solution everywhere. So for example, when we solve the PDEs, we are solving the PDEs even in regions where the density is very small, meaning in practice, when you take n agents, there would be no one, right? I mean, maybe mean field, you see some mass, but in practice, if you take a number of agents, most likely there will be no one there, so you don't really need to learn the control, right? So from that point of view, maybe the FBSD approach really focuses on the path or the region of the space that matters, that you are going to see the most when you go back to the n-player game. So maybe something to explore there, but I don't have a rigorous answer. Thanks a lot for the question. One more question. Do we still have time? Can I still answer questions or we have? Okay. Yeah. So thanks. So, okay. I did a comparison between PyTorch and TensorFlow for the global and dynamic programming solvers. Okay, great. TensorFlow was more efficient in terms of computation as it uses static graphs. Okay, yes, when PyTorch uses dynamic ones, especially when in this setting, the shape of our inputs are static. Yeah, that's a good point. Thank you. So indeed, there are some details about how TensorFlow and PyTorch work. So TensorFlow makes a graph of computation beforehand, and so you can optimize things. So if you check the codes that I'm providing, very often you will see somewhere the decorator at tf.function, and this actually asks TensorFlow to optimize the computation, the graph of computation beforehand. So the first iteration is going to take more time, but after that is going to be faster than if you don't use this decorator. And indeed, in many cases, I think this makes the method faster than PyTorch, possibly. At least in some cases, I have seen that. So thanks a lot for this feedback. Anyway, using the decorator at tf.function is a good idea in many cases if you use TensorFlow. Another question, if we work with reproducing kernels, yes, by the way, there are some papers using kernel methods, but I didn't mention that. So I can add more references later. So if we use reproducing kernel, Gaussian kernel, other suggestions on a library, I am not sure. So to avoid memory saturation when we have a huge matrix calculation, yes, that's a good point. I don't know, I haven't used this technique too much, so this I am not sure. But I imagine you have tried to use the standard libraries and you are hitting memory issues. So, okay, I don't know. I don't have a very good answer for this one. Sorry. Maybe you can contact me later and we can discuss further. The references, yes, I can share some references using kernels and mean-field games. I don't remember right now, but I will double check and I can add it to the slides, either this slide deck or the next one. Yes, definitely. And there are also a few other references. For example, yeah, there are other works. For example, there are some works using both DGM and FBSDEs. I'm thinking in particular about a work by Christoph Reisinger and collaborators. So there are some works doing comparison actually. So I will add this to the slides. All right. I don't know if there are further questions. Otherwise, I guess we can
thank you so much, Mathieu.
Thank you very much.
I think I will stop broadcasting now.
Okay.
And just say that we meet in